Hi, it's Mr. Duffy. Welcome to physics. Today we're going to be learning about kinematic equations. Kinematic just means the study of motion without worrying about the forces involved that are causing the changes in motion. That will be saved for a later unit in physics. The equations that we learn about today will set up a basis for solving a lot of different problems throughout this unit and in future units. So let's go ahead and get started. Obviously, from past units, past lessons, we've learned that graphs, tables, diagrams, those are all very useful ways to solve problems in physics. But equations are also another great way to do that as well. We're going to be learning about 4 of them today, and I'm going to show you how to derive them in order to solve for different variables. Let's go ahead and talk about what variables you would want to know about when we are studying motion. First one we want to talk about is displacement. Displacement is very similar to distance, but again, displacement means the difference from where I started, my change in position, the difference from where I started to where I ended. Now, again, it could be the same as your distance, but it's not always the case. Another piece of information that we would want to study in motion is velocities. Velocity is, again, your change in displacement over your change in time. And it includes, again, the direction in which you traveled. Now, there are 2 different types of velocities that would be useful for us to know. How fast was an object moving when it started moving? We would call it initial velocity. And then an object might move again for a while, and we might want to know its final velocity. Now, it is also quite possible that the initial and final velocities are the same, but that, again, that would be dependent upon each individual scenario. Another piece of information we would want to know or need to know about to study motion would be, is the car or the object accelerating? So we would need to know about acceleration. Acceleration is the change in the velocity over the change in time. We are only studying in this unit objects that are having constant acceleration. Now, these are the 3 basic ones, 3 main portions, but to know anything about the motion, we also need to know about time. How much time was involved in the motion? Okay, again, velocity depends on time and so does acceleration. So that is also kind of a variable that we have to have information about. So with these 4 pieces of information, we can really study motion and use equations to actually analyze what's going on with a particular motion. Let's take a look at a scenario. Let's take a look at what we might need to know if we wanted to know how fast an object was going after a particular amount of acceleration. So to do this, to do this, we are going to derive an equation from our acceleration equation. We have learned about acceleration in the past units. Acceleration is our final velocity minus our initial velocity, all divided by the change in time, the time interval. So what all I really have to do to derive our first kinematic equation is rearrange our problem, rearrange our acceleration problem, and solve for final velocity. So to do that, what I need to do is multiply both sides by my change in time. I'm going to multiply the acceleration by my change in time. And that gives us a delta t on the left equals velocity final minus velocity initial. Now, to get velocity final by itself, I'm going to add my initial velocity to both sides. So what we end up with is velocity initial plus acceleration times time equals my final velocity. This is my first kinematic equation, derived from my acceleration equation. Here it is, written out. Velocity final, again, equals velocity initial plus acceleration times time. Vf equals final velocity, Vi is initial velocity, A is our acceleration, and delta t is our change in time. Let's use this equation in a practice problem. So here's a practice problem. A plane is starting at rest at one end of the runway, and it undergoes a uniform acceleration of 4.8 meters per second squared for 15 seconds before takeoff. what is its final speed at takeoff? So what I'm going to do, and I'm going to set up my problem, I'm going to write out what's given to me in my problem. First off, um, my final velocity is a question mark. My initial velocity, it says the plane starts from rest. So that means it's starting at 0 meters per second. Another thing that's given to me in the problem is my acceleration. It says it accelerates at 4.8 meters per second squared, and that's positive. Again, we don't know which direction the runway is facing, but again, we're just going to assume it's a positive direction. And another thing that's given to me in the problem is it takes 15 seconds for it to take off. Okay, so these are my variables that I'm given in my problem, and I know my unknown variable is my final velocity. Now, the only kinematic equation we know at this point in time is going to be the one that we're going to be using. Our velocity final equals velocity initial plus acceleration times time. I could draw a diagram of this as well, in which case I'm not a very good drawer, but here's my airplane, and it's going down our runway. Okay, and I can label and draw it. But again, some people are very good at visualizing, but sometimes again, a diagram does help. So our initial velocity is 0. Our final velocity is what we're kind of looking for. Moving in the positive direction, our acceleration is to the right. So our acceleration to the right, and the velocity is also to the right. Okay, so that way it lines up. We don't have something, slowing. This is an example of some object speeding up. So at this point in time, after I have a diagram, I have my unknowns, I can plug my numbers into my equation and solve for it. So velocity final equals my initial velocity, which ends up being 0, plus my acceleration, which is 4.8 times 15 seconds. Okay, 4.8 times 15 gives us a final velocity of 72 meters per second. And that would be, again, in a positive direction, whatever that is. So it is a velocity. Okay, so that is our first kinematic equation. Let's take a look at another. Our first kinematic equation dealt with finding a final velocity after a period of acceleration. But what does displacement depend on? Displacement, again, is our change in position. Well, hopefully you realize that displacement would change on our amount of time that we move, the amount of time that the object is in motion. Another thing that you might realize that displacement would depend on would be how fast was the object moving when it started its motion. Did it start from 0 or not? It might have had an initial velocity. It also would reason to expect that we would also want to know its final velocity. And if possible, we would want to know the object's acceleration. If we knew those pieces of information, we could definitely solve for how far the object moved. But let's say we don't have the object's acceleration. Can we still solve it? The answer is yes. I want you to think about the equation for displacement in the first place, or more specifically, let's use the equation for velocity. Velocity is your displacement, your change in position, over your change in time. So if we rearrange that equation to solve for displacement, change in displacement, our displacement, is equal to our velocity times our time. Okay? Now, we can only use this equation if it has a constant velocity. And in this problem, I'm saying we don't have the acceleration given to us in the problem, but we know that there is an acceleration. In which case, if an object is accelerating, we cannot use this equation. But what we do know is we do know that the object has a constant acceleration. I'd like you to think about then, if we instead didn't have the velocity, but if we have the average velocity, that would also allow us to calculate the displacement. So what is an average? Well, an average velocity would be a combination of its velocity initial and velocity final, but we would just divide that by 2. So if we can rearrange or rewrite the equation, for displacement, replacing in the average velocity, this will actually bring us to our second kinematic equation. And rewrite it as half of our velocity initial plus velocity final times our change in time. Okay? Again, just rewritten as half, which multiplying velocity initial plus velocity final times half is the same as dividing by 2. And that's what we have here on our second page. So delta x is our displacement, velocity initial, velocity final, and delta t is our change in time. Again, exactly what I just derived on the last slide. Let's look at an example problem. So, Maggie applies the brakes of her car. The car slows uniformly from 15 meters per second to 0 meters per second in 2.5 seconds. How many meters meters before a stop sign must Maggie apply her brakes in order to stop at the stop sign? So in this problem, what we are looking for is the displacement, how far this object can go, so before it comes to a stop. We know our initial velocity is 15 meters per second. Our final velocity, it says, comes to a rest, 0 meters per second. And the time given to us in the problem is 2.5 seconds. That's how much time we have to stop. Okay. Now, again, the kinematic equation that we would want to use is our change in displacement based on our information that we have is half of our initial velocity plus our final velocity multiplied by our change in time. Again, we're going to have to use this one because no acceleration was given to us in the problem. Again, I can draw a diagram of kind of what's happening. We've got ourselves a car. And it's moving down the road, and we've got ourselves a stop sign. Okay, and the car is moving to the right. Our acceleration is going to be the left, but we don't know that value. But we do know it takes 2.5 seconds to do it, and we want to know our distance, our displacement there. Okay, so let's plug in our numbers. We're looking for our displacement. Half of our velocity initial is 15, plus our velocity final, which is 0, times our change in time, which is 2.5 seconds. Okay, half of 15 is 7.5, and 7.5 times 2.5 is 18.75 meters. Okay, that would be our displacement, and we don't know if the object is moving to the right or to the left, but that would be our change in position from where we initially started. Okay, this one allowed us to find our displacement, so let's look at another. Imagine I would like to know how far I've gone, just like in the last kinematic equation, after a period of acceleration. But in this time, actually, let's write the variables out that we would want to know. We would want to know amount of time. We would want to know the velocity final. We would want to know the velocity initial, and we would want to know the acceleration. Let's imagine that this time, though, I do not know my final velocity. Can I still solve this using equations that I already have? No, but I can derive a new one. So let's go ahead and try that. So I'm going to derive a new equation from the two equations that we already have, we just found. Let me write those on the board. First one that we found was our velocity final is equal to our velocity initial plus acceleration times time. And the last one we just solved for was our change in displacement is equal to half our velocity final, or velocity initial plus velocity final times our change in time. So again, the issue is that we don't have a velocity final. But if I realize that I can, since I don't have a velocity final, if I can substitute in our first equation, our first kinematic equation, into velocity final in our second equation, that will replace the velocity final, which I don't have, with a velocity initial, which I do have, and allows me to, again, solve for my displacement. I just need to kind of clean it up a little bit. So let me replace that in there. Displacement equals half of velocity initial plus velocity initial plus acceleration times time times our change in time. Okay, so now again, I just kind of need to simplify and clean up this equation. Let's do that by first combining some like terms. So our displacement is equal to half. I'm going to combine our two velocity initials. So there'll be two velocity initials plus acceleration times time times our change in time. Now the next thing I'm going to do is distribute in. I'm going to distribute in our change in time to the two factors. Into the parentheses. And then that will give us our next one, which is half our two velocity initial times change in time plus a t, and then this would be squared. So that is factored in now. And now I'm going to factor in the half as well. So then that becomes our displacement equals half times 2 would just be 1. So 1 velocity initial, I don't need to write the 1, times our time plus half a t squared. Now at this point in time, there's nothing else I can simplify. So this becomes our new equation. I've got that nicely written on our next slide. The displacement is equal to our initial velocity times our time interval plus half at squared, half of our time interval squared, half of our acceleration times time interval squared. Let's put this to practice in a practice problem. The driver of a car is moving at 15 meters per second and applies the brake, causing a uniform acceleration of -2 meters per second squared. The car travels for 3 seconds. How far did the car move during this braking period? So again, what we're looking for in this problem is our displacement. That's the question mark. What we're given in the problem is our initial velocity, which is 15 meters per second. We're given our acceleration in this one of -2 meters per second squared. And we are given our time interval. Now, again, what's different from our last problem is that in this problem, we have our acceleration, but we don't have our final velocity. Again, the equation that we're going to use is the one we just derived. Our displacement is equal to our velocity initial times time plus half our acceleration times time squared. We can draw a diagram for this again. We've got our same car. Okay, I did a better car in the first problem. Got ourselves a stop sign. Okay, they're applying their brakes. I'm assuming they're coming to a stop, but maybe they're not going to. We're going to see how long it takes them to move. So again, they're moving. We want to know the displacement. We know that they're moving for, again, 3 seconds, and their initial velocity equals 15 meters per second. Okay, now let's plug in our numbers and let's solve for the problem. Initial velocity, so displacement equals our initial velocity, which is 15 meters per second, times 3 seconds, plus half of our acceleration, which again, it's important that we write -2 on that one, because that is our acceleration, times our time squared. So again, remember to square that value, your time. 15 times 3 is 45. So we have 45 plus half of -2 is -1. And 3 squared is 9, so that becomes -9. So we have 45 plus a -9, or 45 minus 9. So our displacement then would be 36 meters in the positive direction. So again, to the right is positive. Okay, we have one more equation to derive. So Let's go ahead and try that. For our final kinematic equation, I'm going to propose a scenario where I want to know how fast I'm moving after a period of acceleration, which again was the second equation we kind of derived earlier. But now I don't know for how long I've accelerated. All the other kinematic equations have involved time in some in each of the equations. This one, we do not have the time. So again, what do we have? We would have the acceleration. We would have the initial and final velocities, and we would have to have the displacement. Okay, so to do this, to get this new kinematic and the last kinematic equation for this lesson, we're going to take the first two equations that we derived at the beginning of this video. I'm going to put those back on the board. And first one we derived was final velocity equals velocity initial plus acceleration times time. And the second equation that we derived was my displacement equals half of my velocity initial plus velocity final times my change in time. Now, again, what I don't have in this problem is time. I don't have time, but what I'm looking for, again, is my final velocity. So I need to get time out of that equation. To do that, I'm going to rearrange my second equation to solve for time and then substitute it in. So let's do that over here. Let's take my my right equation, the displacement equation, and I'm going to solve for time. Basically, what that means is I need to divide by half. So on both sides, I'll divide by half, and x displacement divided by half as well. Dividing by half really just means you're multiplying by 2. So what we end up with is 2 delta x on the left side, and then we have velocity initial plus velocity final times my change in time. Again, these are being velocity initial, velocity final are being multiplied by time, so I can divide both sides by that. It'll cancel out on that side, and we have velocity initial plus velocity final on the left now. I'm going to rewrite that. So we have 2 delta x over velocity initial plus velocity final equals time. I'm going to take that and plug it in my equation on the left, my first equation that we derived, and then I'm going to start to simplify, which it does take a little while to simplify this one. Velocity final equals velocity initial plus acceleration times 2 delta x over velocity initial plus velocity final. Okay, now what I need to do is I need to simplify this, but the first thing I would do is I'm going to distribute acceleration into the portion that I just solved for time. So that'd be velocity final equals velocity initial plus 2a delta x over velocity initial plus velocity final. I'm going to subtract now velocity initial to the left side. So I'm going to subtract it from both sides, and that's going to give me velocity final minus velocity initial equals 2a delta x over velocity initial plus velocity final. Now, what I'm going to do is I'm going to multiply. I want to get velocity initial, velocity final. I want to, again, simplify that. So I'm going to bring it over to the left side. I'm going to multiply both sides by velocity initial plus velocity final. That's going to, again, cancel it out of the bottom part of the fraction there on the right. And I'm going to multiply it by over here, velocity initial plus velocity final. I'm going to rewrite that, and then we kind of see a little bit better what we've got. So we've got velocity final minus velocity initial times velocity, we'll just write it this way, velocity final plus velocity initial. really matter the way I order it since I'm just adding them together, equals 2a delta x. Now, what you would see is that we've got ourselves two portions in parentheses, and we need to FOIL them. Do the first outside, first, I don't know what FOIL stands for really. I don't teach math, but we need to do the first outside, inside, last, whatever. That's what it stands for, FOIL. Okay. So we're going to multiply the firsts. So VF times VF, velocity final times velocity final, is velocity final squared. Okay. The next thing I'm going to multiply is my first and my outside, I guess is what it's called. So we'd have VF, a positive VF, VI. I'm going to do now my insides. That'd be then minus VF, VI. And then I'm going to do my last. That would be minus velocity initial squared. Okay, then this all equals again 2a delta x. Okay, now we would see here we have a positive VF VI and a negative VF VI. Those are going to cancel each other out. And so now what we're left with is velocity final squared minus velocity initial squared equals 2a delta x. And the last step is I just need to add velocity initial to the other side, because what I'm really trying to, again, show in this equation is my final velocity. So velocity final squared would equal velocity initial squared plus 2a delta x, 2a times our this change in displacement. This is our final kinematic equation. Took us a lot to get there, but this is it. So let's go ahead and show it a little bit nicer and a little neater. Velocity final squared equals velocity initial squared plus 2a delta x. 2a acceleration times our displacement. Let's do one final practice problem. A person pushing a stroller starts from rest, uniformly accelerating at a rate of 0.5 meters per second. What is their final velocity of the stroller after they moved 4.75 meters? So again, we're looking for final velocity here. That's our question mark. And again, what's different from the other kinematic equations is I'm not given a time in this problem. I'm given a distance, travel, a displacement. So initial velocity, starting from rest, so 0 meters per second. Our acceleration is a positive 0.5 meters per second squared. And our time, or our distance traveled, our displacement, delta x, would be 4.75 meters. The equation we just derived was velocity final squared equals velocity initial squared plus 2a delta x. I can draw a scenario of this. So we've got a person pushing a stroller down the road. Nice little stroller here. Wheels. Looks kind of like a shopping cart. And they travel for 4.75 meters. They accelerate at 0.5 meters per second squared. And they started, again, velocity initials rest. Question mark. How fast are they going down here at that? I'm going to draw some little, probably going pretty fast, right? Smiley face here on there because they're going so fast. Okay, so let's plug in some numbers into our equation. Here we've got our final velocity squared equals our initial velocity, which is 0. 0 squared is going to be 0. Plus 2, our initial, our acceleration is 0.5 meters per second squared. And then it accelerates for 4.75 meters. So 0 squared again is 0. 2 times 0.5 is 1. And then 1 times 4.75 is 4.75. So our velocity final squared is 4.75 0.75, but that is velocity squared, our final velocity squared. So we need to square root both sides. And when we square root 4.75, we get a velocity of 2.18. 2.18 meters per second is our final velocity. I know this lesson was a lot, but here is a summary of the 4 kinematic equations that we derived during this lesson. On the left side, we have what we derived, and the problems become a lot easier if objects start from rest. And that's what we have on the right side. Now, not all of the times do the problems actually start from rest. The objects don't always start from rest, but in a lot of problems they will. And so a lot of problems will simplify into the right column of these equations. We are going to practice using these equations a lot. So get used to them. They each can be, again, they all, depending on the scenario of what they give you in the problem, depends on which equation you're going to use. But again, they all are very, very useful, and we'll use them throughout the year. So hopefully now you understand a little bit more about the kinematic equations, and thank you for watching.